Good morning, good afternoon, good evening, wherever you are watching us. This is SDC 2020. Today we're going to tell you about an accelerated AI for Internet of a lot of things, use cases with storage tiering and shared storage at the edge device. Uh, um, my name is MK Jibi. I'm a technical director with NetApp ESG, and my co-author is Mr. Joey Parnell. He's a senior architect at NetApp ESG. For our paper, we have the following agenda. We're going to talk about the current problem where there are limitations in the architecture. We're going to talk about different data pipeline that emerging in AI. Joey was going to go over the shared storage for inference and different concept and use cases, examples, and also logistic and consideration for storage, shared storage and inference. And then we'll share with you the key takeaways from this presentation. The current problem today is on transmitting from Internet of Things to edge devices to a core data center so that you can do intensive AI use cases. Today is costly. And the cost is in terms of network bandwidth and latency. So in order to avoid that cost, what we are recommending as an alternative method is to place hardware resources like GPUs and put those at the edge so that you can perform certain operation locally and reduce any network congestion and latency so that you can prohibit the cost and the power requirement associated with such a network congestion and latency. So that's what we are recommending, adding hardware. Now the presentation will describe the concept behind adding the hardware, the framework for presenting the shared storage to IoT devices, and talk about the different compute-intensive iterative refinement training that can be performed either in the core data center or in the cloud analytic platform. Okay, and updated the AI inference data transmitted back to the IoT device to provide a customized training and to improve the reliability and reduce any false positive rate that can happen. Okay. So what are the emerging AI data pipelines? Okay, so the three major blocks of this AI pipeline is you have the edge device, you have the core, and you have the cloud. Okay. Now, through the use of shared storage by the IoT device, more compute-intensive iterative refinement training can be performed either at the core, okay, or at the cloud, okay, or at the cloud analytic platform. And you updated the AI interference data transmitted back to the IoT device, okay, so that you can provide customized training and improve the reliability, as I mentioned before. So by coming and adding flash storage and extended the shared storage between IoT device, the distributed applications, okay, this can divvy up work to idle as Joey is going to explain later on in examples, or devices that are underutilized. You can share that bandwidth they have and store the result locally and send metadata to the originating device about where to read the result. This will allow IoT devices to coordinate and complete AI tasks that may exceed the computing capability or the latency requirement of the singular device and minimize the data travel to and from the data center. And finally, you can you have a critical IoT data that's transmitted to the core data center, can be either regularly archived to cloud, okay, or protected by some sort of disaster recovery solution in the cloud. What that will do will minimize the risk without significantly increasing cost by selecting using different cloud resources, okay, and also store data on premises and mount that data as a target from the cloud via gateways, okay, via gateways, and also minimizing the risk on certain selective using cloud sources, storage device premises, and mounted on the gateway. This is in order to perform different analytics and transmit back only the result to the data center, okay, or archive it for the long-term retention, okay. Now so when you look at this block diagram, okay, look at this block diagram. The main piece of this paper is the deployment aspect. That's why we highlighted this section, the deployment and the model serving. And Joey's gonna go in details about how's that deployment is gonna be done. Okay, so workload, so workload at each stage. What do we mean by that? We mean that, so at ingest you have raw data that's not formatted. This raw data are sequentially written. So when you come and prep that data, what you put labeling on it, you put associated with pictures, normalize it, you transfer it, and then you transform, and you ended up with those workloads varied so that when you do the explore/training, you have random, raw bandwidth, you have GPU intensive. Those are training GPU that can be powerful and be able to saturate or accommodate all the bandwidth that you need within this method. Also inference, we have testing and deployment for read. We have inference GPUs with lower wattage, that's mean lower cost, okay? And also by implementing where the work is done at each state, depends on what type of use cases. So we'll customize where it's going to be implemented depending on what the use cases are and the industry that's been used. So decreasing time to insight. So when you come and we transmit large raw data set to the core, as we said we're sending the data from the edge devices to the core, so that we can, to reduce the cost on the inference. For inference is costly, and to reduce the cost in terms of the response latency and the network congestion. So that's one, transmitting that large data, moving that large data from block to block, give you that cost reduction. Also moving the inference closer to the edge, allow you to decrease the time so that you can, for actions, for recognizing things and whatnot. And then quickly improve, you'll be able quickly to improve customer experience and drive different aspects of business values that the user is trying to achieve. And with this, I turn it to Joey Parnell so he can talk about the emerging pipelines. Joey?
Yeah, so some of the machine learning pipelines have been changing over time, and one of those changes has been the introduction of doing some inference at the edge device. So some industries are actually already on this journey where they're doing this. An example is there's many video surveillance vendors that are doing this today, and other industries are starting to look at this more. So like healthcare and financials, for example. But so not everybody's at the same place, and I just want to kind of set the stage. Inference at the edge is something that we think our shared storage is going to provide a lot of value for this use case. And these are not just fringe science projects. These are applications of machine learning to specific problems with a clear return on your investment. So this is what is sometimes referred to as boring AI, or things that they're not very interesting sounding problems that we're solving, but they're actually very clear problems that we can solve today. One key aspect of this whole paper is, we have different GPUs for different purposes. There's training GPUs that are beefier, more expensive, higher wattage, power consumption, and then there's inference GPUs that are coming out that are or have been coming out that are smaller, lower total draw power, and they fit a lot more of these edge use cases. So that's where we'll be targeting our shared storage idea. So there's real inference use cases at the edge today. What are some examples? In healthcare, does the patient need attention? That's something you can answer with inference at the edge. Is with either monitoring of sensors, wearables, or surveillance data as well. Is a person or a crowd acting suspicious or threatening? City level surveillance. This is a problem that they need to solve. With surveillance data, does this area need to be cleaned? That's kind of a current COVID use case where someone has been in this area for a significant amount of time, or has touched surfaces. So this is something that we can answer with surveillance data. Is a person's heart rate elevated? That's another healthcare use case. Or is there a manufacturing defect? So supply chain, how can we help the supply chain, with either surveillance data or sensors to know, hey, should we stop the production line? Is there a problem, a flaw that needs to be addressed? So a lot of these things, where we see shared storage providing value is in deep transfer learning use cases, and specifically deep transfer learning at the edge. So there's a lot. I guess transfer learning is where you take an already learned model and you use it to solve another task. So it may be that the other task is very closely related to the original problem that was being solved, or it may be that it's not very related at all. It just depends. But the key is that it doesn't require significant retraining or significant fine tuning. Just a small amount of retraining or fine tuning is needed. And so those are things that an inference level GPU is good at. There's also healthcare, COVID kind of use cases for deep transfer learning, where how can we mitigate a pandemic with deep transfer learning, and how do we do that with the proliferation of devices at the edge, of IoT devices? So those are some interesting references there if you want to read those. Go ahead. So what I'm going to share here is the idea of shared storage for inference, and how can we use that to accelerate these use cases and provide business value for your customers. Go ahead. So we need to rethink the architecture for inference at the edge, and the reason we need to rethink it is because we have this emerging network of 5G and beyond, where devices are going to be either always connected or almost always connected. So what can we rethink, and what can we do differently to maximize our usage of our resources and to provide the best value for our customers? So there's this proliferation of IoT devices that is increasing at like 35% CAGR year over year. So this is a huge explosion of IoT devices. It's been happening for some time, But you combine that with the increased deployment of AI at the edge that we see happening, or that we see happening imminently. Those two things combined, that's going to exceed the improvements of GPUs in that same time frame. So the compute power per watt is increasing, of course, over time. And actually, a lot of research has shown that Moore's law is holding for some of this deep learning and GPU use cases as well. But even with those improvements over time, those are not enough to overcome this proliferation of devices and the increased deployment of AI at the edge. So what can we do and rethink this to do things in a smarter way? So some workloads are actually machine learning workloads are already fine without GPUs. So an example is there are some NLP cases that you can, a CPU, if it can run long enough, is good enough. An example is like, a chat bot that, if it takes a couple seconds to respond, okay. But, most of these use cases require GPUs, but it depends on the urgency of the use case. Your average smartwatch that's just kind of monitoring a health sign, are you possibly having, is your blood pressure too high, your heart rate too high? Those are things that can be done, without a GPU, because it's just happening with, time series data on a small scale. But there are use cases like stadium security where obviously that is a very high urgency of getting that information. If someone's a threat, we want to know right away. We don't have seconds or minutes to wait for CPUs to crunch that data. So GPUs are needed for most of these use cases, but not all. I guess is the point there. And locality of the data matters too. Is network latency going to be an issue? What is the expected performance of your inference use case? Are there service level agreements or quality of service that you're already signed up to achieve, or is this okay that your use case is has a higher latency? Finally, a big consideration is storage space versus the size of your inference data. So what we're trying to do is squeeze the cost out of every device. Obviously, we have this proliferation of devices. If we can squeeze cost out, or by using it more efficiently to spend that money solving your business problem, that is a positive thing. Go ahead. So here's kind of an example today of a committing of an inference model to edge devices from the core data center. So in this case, we have what we're calling a distributor, which is a node in a simple case, we'll say it's in the data center, that is writing out the inference model to the edge devices. It's got that same inference model. It's deploying it to each of the edge devices. And what you have here is many persistent copies of the same model. And on each edge device, it's got that same exact persistent copy. So you're persisting all that on flash parts, using you're wearing out their flash part, writing out that data, and it's inefficient resource use, obviously, because you're keeping all these copies of the same thing. And one other thing you don't have is you don't have this abundance of storage space to store dozens of different copies of your inference models for different circumstances, which I'll get into in a little bit. So you kind of got this limited storage space, and you can't react, and you can't do different kinds of deep transfer learning because you have a limited amount that you can store. Go ahead. So what I'm proposing here is a fetch model where your edge device is going to fetch the inference model from the distributor node. So what we have here on the left is the distributor, and instead of just writing out the data, it's writing out an intent to write the data. So we write out metadata to the edge device, and then the edge device, when it's ready to pull in that model, it will read the inference data from the distributor node and store it in, and it could store it in memory only. It doesn't need to store it in persistent flash, and I'll get into that in a little bit. So what we have here is, we're persisting on each edge device the location of the model, not the model contents itself. And then the edge device can fetch the inference data and store it in memory, and it can actually have several different versions of inference data over time that it's persisting the locations to several of these inference models, and it can load them in dynamically. And it doesn't need to persist them unless you want to for your use case. So what this allows is continuous deployment and rollback of inference models. But more importantly, what it allows is a flexibility to switch between different models depending on your circumstances. So for example, a retail location might have a different model for day and night. If let's say it's a retail surveillance, you don't. There are certain things that you expect that you want to look for during the day versus the night. There's certain things that you want to look for on a weekday versus a weekend, potentially. And then there's obviously new things happening with COVID where you want to look for certain things happening. Maybe you want to apply distancing or looking for areas that need to be cleaned, things like that. But these are things that you can switch flexibly between all these different models, and you don't have to store all of them in memory. They don't have to all fit in memory because you can kind of swap between them using this deployment model. This also enables a lot of non-AI use cases, which is not the focus of this paper, but I'll mention it anyway. You can ship devices from the edge, and you can ship edge devices from the factory without having all the software that you need loaded, and you can have them go and fetch that software later, and that way you can ship from the factory and without having to do a pre-staging or updating of software before you deploy out into the field. Go ahead. Okay, so far we've been talking about a lot of concepts, and what we'll delve into now is some use cases and some more of the concept, extending it into a mesh. So what we talked about is more of a centralized shared storage model, but there's also a natural extension of this is to have a mesh of edge devices with distributor nodes. So in the previous couple of slides, we had a distributor node. Those distributor nodes could be in the core data center, or they could be other edge devices in your mesh. So what you could do is create a grouping of edge nodes, coordinating that work instead of dedicating it back to the core nodes. And you can also do deep transfer learning amongst these neighbor edge nodes, which I'll get into in a moment. This is not a new idea. This is, gets us into what's called fog computing, and there's also some security considerations that we'll talk about as well. But that's the idea. Go ahead. So in a mesh, what we can do is distribute the work across the nodes, and I'll describe that a little bit with an example. So if you have 3 cameras here in this example, 2 of which are receiving heavy motion activity in this field of view, and 1 of which is basically idle. There's no motion occurring. So in this example, you have the resources of 2 cameras being utilized to the max, and you have 1 camera whose resources are not being utilized at all. And what I'll describe here is the way that this idle node, this idle camera can assist with a machine learning use case. And the way that this can occur is following the numbering on the right here, reading frames from the peer node. And the way we'll do this is to write metadata on the busy node to indicate that they're overutilized. So the node on the left and on the right there are going to write metadata to a shared storage region saying, I'm busy. And then the idle node, the one in the middle, can poll its peers to see if any of them are overburdened. And it will see that yes, the left camera and the right camera are both overburdened. So what can I do to assist? So what the idle node can do is read frames from the idle node, read them, and then process those frames using deploying the inference model. So you got your heavy nodes, they can't keep up with the burden, so the idle node is reading frames from the busy nodes, performing to solve part of the inference problem, and storing those results locally on the idle node, and notifying the busy nodes where to read those results and merge them in. Go ahead. So the way we'll do this is, we're distributing the edge devices, and what we're doing is we're using the flash memory to solve these problems instead of storing a bunch of inference models. So, the inference models is in memory, and then we're using this flash to assist and store the results from the problem we're trying to solve. So in this case, it was an inference for cameras. So the applications can divvy up the work to idle and underutilized devices, store the results locally, and send only metadata to the other devices, telling those devices, when you're ready, come and read the results from my local memory. So the IoT devices can coordinate and complete AI tasks, and what they can do is exceed the computing capabilities and the latency requirements of a single device by distributing that work. And we're minimizing the data traveling to and from long distances. So it's not going out to the data centers, not going out to the cloud. It's all just within the that grouping of IoT devices. Go ahead. Another problem that we can solve with this shared storage is we can present the data from the edge device as a target for disaster recovery purposes. So, for example, your core data center is down. We need to have some sort of a backup. In this case, the edge device can actually be mounted from the cloud via a storage gateway, and you can perform the analytics that you were using, some other resource for. You can perform those off-premise and return or archive those results. So this could be a backup plan. You can do this when the core edge resources can't keep up with the demand or are unavailable. And this is a nice backup plan, a disaster recovery capability that you can add through shared storage. Go ahead. Another thing that shared storage enables is flexible mode switching. So, we already talked about how, each part of the pipeline, where that work is done, it depends on the use case. So you have QoS and service level agreements that you have to consider whether your use case is being adequately fulfilled by whatever hardware that you're using. So you can optimize your cost by comparing the cost between on-premise and cloud, between different cloud providers, and you can switch where you're mounting the shared storage from for new inferencing or on existing data. You can switch providers, mount the shared storage, and continue your operations on the fly. So we've talked a lot about concepts and ideas and not a lot about the logistics of it. So we'll jump into that here, and what are some of the considerations as well. So accessing shared data, this is a capability that we can enable by implementing a networked file system on the edge devices. And there are various network file systems. The big ones would be NFS and CIFS, and we'll enable those with S3. But how do we add that support? How do we enable shared storage? We add that support to the edge devices, and that's to the operating systems that the edge devices run. So an example is Android, runs on a lot of edge devices, various real-time operating systems, VxWorks, QNX, there's a laundry list of them, but how do we enable these use cases? It's by enabling network file systems in edge devices, but there's an obvious trade-off here between, you know, having a small deployment with a real-time operating system, which is obviously a key consideration of real-time operating system, versus having a rich feature set that you can provide with, you know, bundled with your real-time operating system. We want to provide the shared storage that for use cases where it makes sense. There will be cases where it doesn't make sense, but you know, where it does make sense, we should include these network file systems in the real-time operating systems. And on the left side here, you know, what we're showing is each edge device. Today, it's kind of one big lump of dedicated storage. We're proposing to divvy it up into two chunks, one of which is dedicated storage for the device, the other of which is writable by the device and readable by other devices within the group. So that's your shared storage region. And what we'll do is have a polling model where the peers can poll. So the local device writes, the peers can poll and read data. And then what we're doing is basically transmitting metadata and allowing us to it's a poll model where we're reading in data from other edge devices. Go ahead. A big problem posed by shared storage is how do we make sure that it is secure? You know, shared storage that can be accessed by anyone, is this acceptable? Well, it's probably not for most use cases. You know, the inference model, the software that's running on the edge device is the valuable intellectual property of the companies who have you know, manufactured and deployed that hardware, and you know, the ISVs who have placed their software on those devices. So it's not acceptable that anyone can read or write to these devices. So we need a security model that can allow edge devices and storage nodes to trust one another. We need certificates, chains of trust. We need you know, something that is standards based, you know, security for edge and fog computing. And we need you know, we need to enable things like HMAC or AES to allow us to trust one another without a man in the middle. And we need a data encryption model that supports that as well. This is an area of deeper investigation. There's actually some literature out there on this, basically security for fog computing. So, but there's a lot of opportunities for increasing the security, and there's opportunities for the storage developer community to help. Go ahead. Dr. Jibby, I think you're going to take it from here.
Okay. So if we look at other consideration for AI and M and machine language, there's the ability to audit, also look at different compliances rules that depend on the type of industry here being used. So you have the personal identifiable information, you have on-prem versus cloud, you have, you know, how long you're going to keep data, retention requirements. Those are compliance things that to consider. Also, being able to reproducing, ability to reproduce, and also there are some federated learning capability that could be implemented here or considered for AI and ML. And of course, you know, there's address fairness and certain bias and bias concern that's really apply to social ethics as well as social ethics. So these are considerations we're going to look into. So as you can see that Joey went and talked about the shared storage area for inference, the concept and use cases. Also, he covered the logistic and consideration. These mainly looking to see how can we satisfy in real time the IoT AI use cases, so in such a way that dissatisfied with a higher fidelity than what it is today, and without increasing the cost by providing a shared storage area in the IoT devices so that allow other devices to perform work, like we saw the example that Joey gave about the idle camera can read from the other two busy cameras and use that resources. That is a more effective use of the resources that the user have, and also remotely update the local inference models. Now, also instead of saving memory, we added a layer of flash to the IoT devices for data tiering, and also provided the capability so that we can perform AI tasks in a very distributed fashion, okay? And this is also not only distributing the work, like the example of the slow cameras, also different activities, not just cameras. Underutilized component within the system can use its resources to help ones that are extremely busy. Also, protect valuable IoT data, protected at a lower cost by using certain selective resources from cloud. So in the area for archive and disaster tolerance, and also for even for recovery in a disaster situation. So you can see that the method seems to be extremely beneficial in the AI and ML world. For references, we listed here all the references that have been used. Very good articles to refer to. We reference them in our presentation, and those things that can talk in detail about certain areas we didn't talk about, assuming that there is some level of understanding of AI by the audience, and that's why we try to spend more time on the concept of the idea. But these are references provided for you. Would like to thank you for attending our presentation, and we appreciate it if you take the moment to rate this session, because your feedback is very important to us. Thank you and have a good day.